Hey, and this fifth installment of Advanced J1939 going to take a look at the receive component of the CAN transceiver. The transmit component, as we talked about last time, some device like a microcontroller that's outside of the CAN transceiver will send a signal or provide a signal when we want to transmit. So we're going to transmit either a logic 1 or a logic 0. So either driving the CAN bus so that the difference in voltage is approximately 2 volts or 0 volts. And so those correspond to the dominant and recessive bit. So the other component of the CAN transceiver is the receive component. So this receive line would go back to the microcontroller. We would then be able to read whether, if some other device is transmitting on the CAN bus, we would be able to receive a message. We need to not start a message if somebody else is already sending a message. So that's one function of it. The other function we need to do is we need to read our own message as we send it out, just to make sure that somebody else hasn't started sending something that's more important than our message. That's called arbitration, and we'll look at that after we learn how this receive component works. So on the CAN lines here, the CAN high and CAN low, this receiver, as it's called, this symbol is generic for an amplifier in electronics. So this is just a generic amplifier. These are often called op amps for operational amplifiers, and they can do a variety of math operations. That's where the word operational amplifier comes in. So I could use this as an amplifier which looks at the difference in voltage. So I could look at the math operation being the difference. I can also use it as something that adds, or it multiplies, that integrates or differentiates if you've taken calculus. So it's capable of doing all of those things. They are fantastic components. They're what allows a lot of the technology that you have probably grown up with to be in existence. So operational amplifiers, won't go into a great deal of theory on them. Hey, looking at this receiver symbol, as we indicate, this is something that can give us a difference in voltage. We could design this so that it would provide a difference in voltage between CAN high and CAN low. And so what we can do with that is we can either cause this transistor, which would give us 5 volts, or this transistor, which would give us ground, which would be 0 volts at this pin. So to make it simple, we'll say that if we put a logic 0 in place here, a logic 0, as you recall, is going to have a difference in CAN high and CAN low of approximately 2.5 volts. We could design this so that the receive out would also give us a logic 0. So that makes it easy for us to take a look at this. If I put a string of 1s and 0s in, I would expect to see the same string of 1s and 0s at the receive pin. Okay, let's take a look at the simulation. And what I've done here is I've put some of these components in place here. I've simplified this a little more. We have our TXD pin, or our transmit pin, which would be this pin, and we have an RXD, which is the receive pin, which is here, the RXD. So if I look, the TXD works the same as it did before. If I put in this string of 0s and 1s, I expect to see this out on the CAN. The way that's going to happen is I'll look at this difference. This is that amplifier, or the amplifier which provides a difference between, so it's basically this input, the plus, minus whatever's at the minus input. So if we figure that we have this at about 3.5 and this at about 1.5, we would expect the difference in voltage to be about 2 volts. I'm then going to compare whether or not 2 volts is greater than, whatever's at this input is greater than this reference voltage. The way this device works, this is a digital device. If the plus voltage is higher, it's going to provide a value basically of 1 volt out. If the minus voltage is higher, it's going to provide a signal of 0 out. Then this device flips that, it knots it. So if I put 0 in, I get 1 out. If I put 1 in, I get 0 out. And what this does is it allows us to put this back into the rules of J1939. So I've kind of done this, to simplify it. So what I expect is TXD and RXD to be the same digital value, so either 0 volts or 1 volt. So let's go ahead and run the time domain simulation, and we'll take a look here. So starting off, we had our first, we wanted this to be our a logic 0, and there we go, we have a logic 0. We have here a logic 1, and and looking at RxD and TXD, both of these are sitting on top of each other, so we can see that they're both exactly the same. So when I sent whenever the bus is idle, it shows us a value of 1, which indicates that the bus is idle. Once we send that first logic 0, we put the logic 0 on the CAN bus for the dominant state. What that does is we can see that the output is being driven to 3.6 and 1.4 on CAN high and low respectively. And the same thing now to drop back down to a difference in voltage of approximately 0. So here's our logic stream. So we have our 0, our 1, our 0, our 1, the 0 and a 1 and a 0 and back to a 1 again. And we can look at these values even though they had decimals behind them. Let's say that this is either a 0. Let's go back to our circuit. Let's take a look. And what we've done here, the same thing that we've transmitted, we've also received. So this indicates that we're able to use that bus. Nobody has interrupted this, as we'll show in the next in the next installment. We'll start talking about arbitration, which is a very important part of how CAN works. We could not have CAN if this ability to detect that somebody else has a message that is more important than mine, and we both started using the bus at the exact same instant. So this is we'll explain how that works. So to review this again, if we look, we have the transmit, we have the receive. We've talked about both of those now. I would expect the logic, not necessarily the exact voltage, but the logic of what I put in for TXD, whether I put a 1 or a 0 there, I would expect to see the same thing on RxD. And if I don't, then that tells me that somebody else is putting information out on the CAN bus, and that if it's more important to mine, I need to stop my TXD. Otherwise, we're going to have a data collision, which should be really bad. So this is part of or leading up to what we'll talk about arbitration on the next installment.